Here we go. Hi, and welcome to our 9 a.m. press conference, The Cost of Increased Smoke Exposure. Our speakers today are Jeffrey Pierce from Colorado State University, Katelyn Odell from Colorado State University, Ebrahim Eslami from the University of Houston, and Manvendra Dubey from Los Alamos National Laboratory.
So thanks. So I'm going to start things off by talking about estimates of wildfire smoke and associated premature mortality or early death. So before I really get into things, I want to acknowledge Maria Val Martin, who really led the future smoke modeling here, and Bonnie Ford, who led the health analysis that I'll show. So smoke can impact large fractions of the US and many parts of the world. So this is a picture from September, a satellite picture from September, where fires in the western US led to smoke that covered a large fraction of the US. I'm going to focus this talk on fine particulate matter, or PM 2.5, and on many days, particularly in the US West, PM 2.5 can be dominated by smoke. So this is from Wenatchee, Washington. This is the PM 2.5 concentration from this past summer from May through October. And as you can see, from May through July, the concentration of PM 2.5 never exceeded 10 micrograms per meter cubed. And in a moment, I'll show you that that's not that high. And then in August and September, when the wildfires started, the concentrations regularly exceeded over 100 micrograms per meter cubed. So just huge changes in the PM 2.5 concentrations. We know that PM 2.5 is bad for your health, and Katelyn's going to go into this a bit more details on this in a moment, but the World Health Organization's daily PM 2.5 concentration guideline says you should keep your PM 2.5 concentrations below 25 micrograms per meter cube, but as you can see, on many of these smoky days, we're exceeding that. So along with the daily smoke days, these smoky days in many parts of the country have a big impact on the annual or long-term PM 2.5 concentrations that people breathe. So even if you smeared this out over the whole year, you'd notice it making a big difference. And so we know that from many epidemiological studies that long-term exposure to PM 2.5 contributes to premature mortality or early death. So this is just from one of those specific epidemiological studies showing your relative risk of dying and how it increases with your long-term PM 2.5 average concentration that you're exposed to. So if smoke is taking you from, say, 8 micrograms per meter cubed to 10 or 12, this is pushing you up this line, so your risk of dying on any given day is higher on average. So the focus that I'm going to talk about in this talk is on the long-term mortality risk of smoke. And Katelyn's going to talk a bit next about the short-term impacts and what this means for hospitalizations and asthma refills next. So regarding climate, this is from a recent paper by Westerling that shows in black this mean spring-summer temperature of the western US over a 40-year time series, as well as in red, on this axis, the number of large fires in the western US in each of those years. And as you can see in both of these time series, there's a gradual trend with a lot of interannual variability. And the temperature time series can explain roughly 50% of the fire time series. So this implies that there's some temperature or climatic influence on fires. And the hypothesis here is that warmer spring temperatures lead to earlier snow melt, warmer summer temperatures can dry out the wood even more, and you can get even more fires. So the question that our group's been working on has been, if we continue to warm, what does this mean for future fires? What does this mean for smoke? And what impact on mortality might this have? So I'm going to just show sort of a single initial analysis on this, and then sort of give some caveats at the end about what we need to do next in terms of this sort of modeling. So step one in what we do is we need to predict future fires. So to do this, we use the NCAR's community land model, where we're predicting, it has an online fire module. So we're looking at how vegetation changes and how fire changes. And we're looking at different types of fire and how they might change. And two of the big things that we really need is we need future climate information. So we're using climate projections from atmospheric climate model simulations that tell how rain is going to change, how temperature is going to change in a region. And we'll use different simulations that say are ones that have little greenhouse gas mitigation and some that have maybe moderate greenhouse gas mitigation. We see how sensitive the fires are to this. We also need to look at how population and things like gross domestic product change, because people, as you move into a forested region, they can start fires, but if you're people and you have enough wealth, you can also fight fires. So things like population changes are also going to be important in the future. Not as much in the US, but more so in the developing world. with this information, we can get projections of how global area burned might change, or area burned over specific regions are going to change. I'm going to focus on the US, though. So using this from our fire projections, we look at how things from wildfire or other biomass burning emissions will change. And we also need to look into the future at how anthropogenic emissions from traffic or industry might change, and other things, in looking at future climate, and how this will impact future air quality, and in this case, particulate matter concentrations. So these are the results over the US for how PM 2.5 from wildfires only will change, or from fires only, excuse me. And so in 2000, this is what our simulation looked like. And we have wildfires in the West, showing particularly affecting Northern California, Washington, Idaho, Montana. And we have fires in the Southeast. A lot of these are prescribed burns where people are intentionally burning fuel, so we don't have a wildfire, but there are also some wildfires there too. In our projection, as we move towards 2100, we see the intensification of fires in the West, a large intensification in the Southeast, as we actually are predicting more wildfires, and taking more emissions than the prescribed burns. And as well, Canada has a large increase in fires, particularly due to earlier snowmelt and a longer time to dry out the fuel. And this can impact the northeastern US. So when we put this together with how other sources of particulate matter will change, we get maps that look like this. So this is total PM, anthropogenic, fires, and other sources. And in 2000, we're actually quite a bit dirtier than we are now, because we've actually taken a lot of these industrial emissions from this region and already reduced them by 2017. But we will continue that trend of, at least we're projected to continue that trend of cleaning up anthropogenic pollution. But we have to overlay on that the increases in wildfires in the Southeast, in Canada, and in Western US on top of that. And so what we see is sort of maybe if you average over the whole US, the particulate matter isn't really changing, but we're changing sort of where it is. We're actually making things sort of cleaner in maybe the Ohio, Detroit region, but making things worse in the places that are being prone to wildfire smoke. So in terms of what this means for health, so we can go back and use what the epidemiological studies have found and then map this PM now into health. And this is summarizing things across the whole US. So this is the fraction of deaths in the US that we can attribute to particulate matter exposure using those regressions. And across all the three different time periods I'm showing here, 2000, mid-century, and end of century, it's roughly 4% of the deaths we're finding. But what's changing is the source of the particulate matter. So the green is all emissions other than fires. The blue is people in the US being exposed to smoke from fires that were in the US, and the red is people in the US being exposed to fires that were outside the US, mainly Canada and Mexico. And as we move throughout the century, this projection shows that we are reducing the anthropogenic emissions, so we're making cars and industry cleaner, but we're essentially balancing that by an increase in wildfire in this projection. And so put in this in absolute terms, we project using the function that we use roughly 25,000 deaths per year in year 2000 from wildfire smoke, increasing to about 75,000 deaths per year. These are slightly larger numbers than what Ebrahim's going to show in his talk, and this is largely due to us using a concentration response function, one of those epidemiological functions that's a recent one that has a higher attribution of deaths to particulate matter. So some final remarks. The main take-home, the one single take-home, is that from our prediction, we predict the U.S. particulate matter to remain approximately constant in the next century, averaged over the U.S., but the smoke increases are going to be compensating the air pollution reduction. And then two major caveats I want to give. This is one single climate projection. It took a lot of computation power to do this. What we need to do now and moving forward is do like what the climate modeling community does and use ensembles and many different models to look at sort of what sort of features are robust across many different simulations and many different model uses. And the other thing I want to say is we've only used one health estimate from PM 2.5 mortality relationship that is good for all sources of PM 2.5, but aren't necessarily getting the differences between industrial PM and wildfire PM. So that's important too. So we need to continue this as well as looking at many different projections of future climate. Thanks. So do we now just go to the next speaker, or do we? Okay.
Hi, my name is Can you hear me? My name is Katelyn Odell. I'm from Colorado State University, and I'm going to be talking about quantifying the health impacts of short-term exposure to wildfire smoke. I first just want to acknowledge this is a huge team effort. This is a team that I work with, both epidemiologists and atmospheric scientists. I also just want to point out my advisor, Jeff, who just spoke, is here today, which is why he didn't get a picture on this team slide. So as a lot of us probably know, there were a lot of wildfires that impacted California earlier this year and are impacting California right now as we speak. This is a satellite image from those October fires showing a lot of smoke impacting the city of San Francisco. And so on a day like this, what our work really wants to know is what are the short-term health impacts that are experienced by the population. The reason we want to know this is so that public health agencies can inform the public of risk of smoke exposure. And so the way that our project works towards that is we seek to identify specific health outcomes and identify populations that are especially sensitive to smoke. So in order to understand the short-term health impacts of smoke, we have to understand two main factors. First, on the atmospheric science side, we need to know who is exposed to smoke and when, and then how much smoke were they exposed to. And then on the epidemiology side, we need to know what health effects are experienced by the population that is exposed to smoke. So first, talking about the atmospheric science side, in order to answer those two questions, what we really want is a map kind of like this one on the screen, where the darker red colors are showing higher smoke concentrations. And so we know that people that live in those darker red areas are breathing in higher concentrations of smoke. But there's several challenges to getting a map like this. First, smoke can vary greatly in time and space, so although this map looks like this on one day, it could be totally different the next day. Also, surface-based particulate matters are often sparsely located, especially in the western United States, where we typically have a lot of wildfires. And in order to understand the health impacts of specific smoke, PM2.5, we need to distinguish that from background smoke or background PM2.5 that would normally be in a city versus what is elevated by wildfire smoke. And to overcome those challenges, we combine multiple data sets to get a better estimate of smoke concentration. So we look at and combine data from satellites, surface monitors, and computer model simulations that use meteorology and chemistry to estimate pollutant concentrations. And by combining these data sets, we get a better estimate of smoke, and we get that continuous map that we need to identify the exposed populations. So now talking about the epidemiology side, where we need to know what health effects are experienced by the population, there's several challenges to this side of the work as well. First, access to health data can be pretty limited, and health data can be sparse and sporadic, especially when wildfires occur in remote regions where there's not as many people. We also can't see all potential health outcomes. So in this work, we're looking at doctor visits and medication refills, but there's other things that we just don't see. So when we are trying to identify, like Jeff was talking about, concentration response functions, we're looking at something kind of like this, where we have an elevated amount of smoke one day corresponding to some disease marker. So this is the number of inhaler refills in a specific city. So we investigate multiple potential health impacts to find those that are impacted by smoke. We focus mostly on the ones that we know respond to urban PM2.5, so respiratory and cardiovascular diseases. So this figure is showing concentration response functions for a select few of those diseases that we look at, and this is an elevated response with 10 micrograms per meter cubed of smoke. So anything with uncertainty that falls above that zero line has a significant response to smoke. So here, that's going to be the inhaler fills and asthma. And these are results from studying the Oregon 2013 wildfire season. So like I said, these responses are for 10 micrograms per meter cubed of smoke, but oftentimes wildfires produce concentrations that are much greater than that. Like Jeff was saying, a lot of times it can be over 100 micrograms per meter cubed, and we would expect the health response to scale up with that. So to take the example of the inhaler refills, again, this is from Oregon 2013. We found that there's about a 7% increase in inhaler refills for the population with the 10 microgram per meter cubed smoke day. But if there's a 100 microgram per meter cubed day, we expect that that would go to over 100% increase in medication refills for the population. But this work is only the tip of the iceberg. We're still looking into other possible health impacts of smoke, like cardiovascular outcomes, by looking at other fire seasons. We're also only one team. There's a lot of other teams studying smoke. And like I said before, we only see a few health impacts, so we're only looking at hospital visits and medication refills, which is kind of the top of this little pyramid over here. But if we're seeing a signal up here, that means there's probably a lot going on further down, things like school, kids missing school, people missing work, people having asthma attacks, and those would affect a larger part of the population. So the impact of smoke exposure is probably a lot greater than we are even seeing in this research. Thank you.
No, it's not there. No. Yes. Good morning, everybody. My name is Ebrahim Eslami. I'm a second-year PhD student of atmospheric sciences in the University of Houston. Today, I'm going to talk about health and cost impact of air pollution from biomass burning over the United States. This is our group work in the University of Houston and funded by U.S.A.'s grant and TCQ Biomass Burning Fund. So as my colleagues mentioned, the biomass burning can significantly degrade air quality, especially particulate matter. As a result, it can adversely affect human health. Here's an example of recent biomass burning events, North California fire case. You can see this is the image seen by Moody's satellite, and this is the air quality index associated with the September 3rd. You can see in North California, the AQI level stayed at the critical level all day. So that's a problem with the biomass burning, as Jeff and Katelyn clearly mentioned. So at such event, by calculating emission and taking meteorology into account, we can model this biomass burning or wildfire event. We can check we can evaluate our model using air quality monitoring network, or we can use the monitoring network as a reference of a pre-wildfire event. And using this system, we can see how much air pollution concentration changes due to a wildfire event, for especially particulate matter, ozone, nitrogen oxide, etc. Using this knowledge, we can model health impacts, and we can estimate health impact incidence and economic cost valuation. For example, our output could be number of hospital admission, ER visit, work loss day, respiratory system, and anything related to health caused by air quality degradation by wildfires. So for our study, we use BEMMAP Community Edition. BEMMAP is developed by EPA and used for various national and regional cases throughout past decades. BEMMAP is a GIS-based open source software that estimates health and cost impact of any changes in air quality, including biomass burning. So BEMMAP sees the changes in air quality. Using that calculation, calculates the changes in population level exposure to air pollution. So it can calculate the change in health impact incidence. After knowing that, we can estimate the cost valuation of these incidents. So we modeled the biomass burning events of between 2011 and 2014 using a state-of-art air quality modeling system, CMAQ. These are the annual mean of wildfire attributed PM2.5 concentration for these 4 years over the United States. You can see that the air pollution degradation were more significant in 2011 and 2012 compared with the other 2 years. And as Jeff mentioned, we have a lot of air pollution degradation in southeast and northwest United States. And in some regions, for example, in North Florida, we can see more than 5 microgram per cubic meter increase in annual mean of PM2.5 concentration. So this is huge. So these are the results by BEMAP health and cost modeling, modeling of wildfire events. The top left is the mortality estimated by BEMAP. BEMAP estimates between 4,000 to 5,000 premature deaths attributed to biomass burning only. And BEMAP also estimates between $40 to $50 billion economic valuation of wildfire attributable PM2.5 related premature deaths. As another example, BEMAP estimates hundreds of thousands work loss days caused by air quality from biomass burnings. And this cost us around less than $100 million per year related to these incidents. So these are only the few examples of BEMAP output. BEMAP can produce a huge variety of details in terms of the cost, health and cost modeling of any kind of air pollution related study, including biomass burnings. So thank you very much.
Which is right and left. Let's go. Oh, there we go. Okay, good morning. So as the three speakers before, I'm Manvendra Dubey, I'm from Los Alamos National Lab, and as the three speakers talked today, they sort of gave you an update what we can do today. So we've come forward in terms of monitoring, and we've got a monitoring network, U.S. and worldwide, and there are models that actually forecast these things, and under extreme conditions, you even issued evacuation orders, not just for fire risk, but also for smoke, and they're published on TV. So I think that's the good news. The challenging news is actually fires will increase largely because of both a combination of changing climate, forest management, and people movement. So I think it's important as these things happen, not only do we keep using those tools, but also refining them. So the work I'm going to present from Los Alamos National Lab is sort of more forward-looking, is how can we take these models and solve, I'll talk to you a little bit about what the challenges are and what we're doing in the laboratory and the field, and using instrumentation advances to dig deeper into what is the toxicity of these smoke particles. So just to tell you my story, I actually grew up here in India, so we live with smoke. I moved to America, more than almost 35 years ago, and I live here, and what I feel I've smoked is I've been exposed to smoke regularly here and sporadically here, but pretty extreme smokes. Los Alamos has had a couple of fires, and actually we were evacuated, but we stayed there for a week. Typically you go there in smoldering fires. You get exposed to a lot of smoke. I know it because I was coughing. So you can see all these fires are actually very different in nature. So the western here, you got these coniferous, mixed coniferous plants burning. Here you basically got a lot of rice and agriculture, and this is laced and mixed with whatever urban pollution you go in there. And all of these boreal fires, African, this is dust also that can be mobilized. So the thing is, it's a global problem, and I think U.S. is obviously concerned about it, and I'll try to give you a quick overview of what, oops, how do I get there? That's good, right?
Is that it?
Is it? Okay, which one? Oh, just a button, is it?
Yeah, just the that button.
Okay, got you. All right, so this is just a fire trend, and you can see that this is the U.S. fire trend, and you can see that in the 21st century, we've had, even the last decade and a half, we've had more and bigger fires and more extreme fire behaviors. There's expanding urban fire interface, so people move, and that's an important component of climate change. It's not just climate change, it's superimposed on that, you have demographics. And actually more important in the US is there's more control burns. So the fire service is to manage is going to do more controlled burns. That creates a dilemma because when do you burn, what is the liability in terms of smoke exposure? I don't think we've visited all these things, so we need to have some tools to assess them. And I think the Forest Service, to the best of my knowledge, is concerned. And then obviously there's a wildfire connection to climate, which Jeff talked about. Okay, I'm not doing it right. Oh, that, okay, thank you. All right, so this is actually a paper it came out in Nature Climate Change, and what this shows you is basically a change in that the human exposure to wildfire increases in the future is a lot from projected population growth in areas with frequent fires rather than just a burned area. So this is dug deeper into, and you can see in the US, in the future, there's going to be a lot more exposure here in the near field because of the combination of human exposure. So this is the probability of low fire regions that become fire-prone, that's the red increase, and fire-prone areas that transition to low fire state. So this is kind of an ensemble mean, as Jeff said, but this now includes demographics and other things. So this is the best we know what we can forecast what the fire risk will be that. And I'm still, okay, there we go. Okay, and this is just a summary. This is kind of what we do. And actually, this is a good story. I think wildfire smoke is a recognized problem, and smoke in general, particulate, urban air pollution. And their operational air quality forecasts, not just in the US and Europe, but actually in China and India. So these maps are global. In fact, even Indians now see these maps and can respond. So that's a good thing. And here I'm just giving you a sample. As you can get the forecast PM10 exposure, PM2.5 exposure, and that's about how deep we get. I think what I will say is you can actually dig deeper because the finer particles can get more into your system, and so PM1.5. And then the question becomes, each PM is not equal. You dig deeper, what are the chemicals in there? So I think we're at the stage where we can actually address those things and improve these things. And then there are gases also. So the challenge is the emission factors. So a couple of things. So when the modelers show you things, they need numbers. So they use emission factors for primary emissions. They also have secondary things like ozone. And all these things require data and measurements. One important caveat here is smoke is actually not just emitted directly in the near field. You see the particles. But actually, it also makes, once a fire plume goes out, it actually makes smoke due to chemistry. And that's extremely important. That can be as much as the smoke in the far field. So there's near field, far field, and these things are and I think most of the models do not account for that for operational models. So this is, again, research to see how much smoke is made as the plume good. The other thing is all these exposure studies use fine-scale models. So fine-scale, they require fine-scale predictions by living something, but the models are coarse. So they will systematically be higher. So how do you resolve, and perhaps you can even locate, if you're developing, you can actually factor these things in when you design where people are going. So more, how do we become smart about where we move? We can live in a forest, but maybe in a certain region of the forest. So those things come up. And again, so I would say currently there's a lot of uncertainties. You have a factor of 2 lower smoke from secondary organic formation that makes in the plume. The resolution is coarse. And those will factor into the risks that we've been talking about. So let me just pose you some questions. What are the science gaps? Since I think we are here to answer these questions as researchers. So again, what I'll show quickly in results is what burns matters. So what wood type is burning? So grass, wheat may not be the same as a coniferous forest. There's also soil mobilization. Structures. So if structures burn, that's obviously soil toxic. We've heard of that in California. How they burn, so a lot of the emissions come from not the flaming fire, but the smoldering fires. So flaming fires are actually less important, and smoldering seem to be more. But flaming can loft these things, so there's how far these can go. So when they burn, so night versus windy. So if you are looking from an air quality point of view, you may want to burn when it's calm. And less windy, but then the fire spread. So we actually have to look at these trade-offs when we manage fires. And this is important, and firefighters do it, and we help them at Los Alamos do some of the modeling. High spatial resolution, so coarse models dilute reality. There's complex terrain, so there's pooling effects and everything that need to be resolved. And then we need to really need to chemically resolve toxicity beyond PM 2.5. So what I'll talk very quickly what we did, and be very quick, is we resolved water solubility. So what fraction of the smoke actually is incorporated in clouds? Is water-soluble stuff more toxic or less toxic because it gets into your lungs? Those are the questions. So you need to understand how the smoke interacts with humid environments, including our lungs and our bodies. And again, air smoke can be more toxic if it survives cloud processing. And net exposure from wildfires, which is loss, versus controlled burns, which is liability. And again, science tools have advanced to address these things. So this is a summary of basically how much water a smoke takes up. And these are various southwestern western fuels. And the point here is you get a diversity of smoke types that interact with cloud and water and probably lung humidity in very different ways. So these fuels like these top one salt center, things that have salts actually become much more take up a lot more water than things that don't have ions in them. So this can help in terms of the lifetime of the smoke that the modelers try to model. This is another slide. Let me see. This shows you that this property of water uptake changes a lot as you go from evergreen needles to halophytic salts, these sort of invasive species which are encroaching. You get a transition in these being relatively low hygroscopicity and these being high. So different fuels will survive different times and have different interactions, and it's good to understand. And models can treat them if you give them these kappa parameter that treats all this stuff. But the key finding of our work here was very simple, which is this kappa parameter is how much smoke of the fuel and or the smoke. So as the ion concentration of the smoke, lifetime and human health. So what I'd like to close here a little bit is the lab has, we're at Los Alamos, and there's a series, we have one, but there's a series of instruments that have evolved that allow us to actually look at smoke. So this is a soot particle aerosol mass spectrometer, and we've been actually running it for the last 3 months, thanks to Los Alamos investments, strategic investments, the particles. It's no longer PM 2.5 or PM 1, it's what else is in there, cesium, rubidium, strontium. So you can measure a lot of these elements that can allow you to dig deeper in what part of these fires are toxic. And again, this is a research tool that can allow you to say more about the toxicity. Here we actually sampled some of these fires from the Pacific Northwest and local fires in Los Alamos. And what I'm trying to show you is we can differentiate very clearly what smoke came from where chemically. So this is smoke that came from Pacific Northwest. Wood has levoglucosan, that wood was all gone. The levoglucosan came over a long environment. So when you have these issues of multiple fires burning, some are controlled burns, where did you get exposed from? So we have to be aware of the regulatory. So these kind of tools can help. Not only do they get deeper into toxicity, but they can also help with, and so we're actually begun doing that. And finally, this is really actually exciting because, so this is, I told you, so this is fresh smoke, this is aging smoke, this is particle chemistry, so this is actually SOA. This is smoke that is generated as the fire moves, primarily from the gases emitted and the reactions in the atmosphere. And this is actually a bioassay, meaning this is now, so we're advancing, we're going a little bit beyond epidemiology. We're looking at a mimic and looking at biological activity as measured by this horseradish. I'm not a biologist, but this is an assay that is a measure of what some biological. And you can see that as this goes up, and this follow the black line, so as the smoke ages from fresh to aging, the response of this test, which is biological, is it actually increases and then begins to fall. So there, air smoke is actually the toxicity of air smoke can be greater, can increase with aging. And these are the kind of questions that actually will allow you to do the next level of iterations with the model. So this can be prescribed in models, just so Jeff showed you. So thank you.
Okay, great. We'll now take questions.
Seth Borenstein, Associated Press. Actually, first for Jeff, your figures of 25,000 PM 2.5 deaths from wildfires in 2000, and you're saying that's 4% of the PM 2.5 deaths. overall in the U.S.?
The 4% was that 4% of the deaths in the U.S. can be attributed to PM 2.5. So it's essentially.
Oh, it's not 4% of the total PM 2.5 deaths.
Yeah, it was like 15% of the total PM 2.5 deaths.
Okay. I was going to say, because I did the math and it looked like you were saying there's 600,000 PM 2.5 deaths a year, and that doesn't sound right. Okay, so given that right now we still have one of the worst, top 5 worst wildfires going on in California history, in Southern California, can you tell us anything? Can you relate your research in any way right now to what's going on at the very moment? Not even the earlier fires of this year, which I know you look, but what can that tell us about the health now? Health situation now for the people of Southern California, and then if we're going to see this more often type of thing, how that affects the health there.
Sure. I almost think this draws upon Katelyn's work a little more, so if you want to jump in, you can. But I was looking, I haven't, unfortunately, just from being here and being really busy, I haven't followed a lot of the smoke concentrations this week, but I was following last week and looking in the region between Santa Barbara and Ventura and that area, and their smoke concentrations were on the order of 200 micrograms per meter cubed, which by going by Katelyn's numbers means we would expect hospitalizations for certain diseases, respiratory diseases such as asthma and asthma refills, to be, at least when you have a large population and a large number of people, you start seeing that to be on the order of doubling. If you want to add to that.
Yeah, I think just going off of like what Jeff was saying with the respiratory stuff, we've done a couple case studies so far in Oregon and Washington. We haven't looked at anything in California, but the respiratory responses, specifically asthma, so medication refills for asthma, hospitalization for asthma, urgent care visits for asthma, are consistently indicator or consistently respond to smoke. So there's a significant increase for that. So I think maybe with California, it would be reasonable to expect that there would be at least that response to the smoke as increased asthma responses.
And what about deaths? Since Jeff, you looked at deaths.
Yeah, so our groups we've partnered with the CDC, and we are currently doing epidemiology to look at the short-term time series of effects of deaths to smoke. And so essentially, like, if you look at when it was smoking in the short-term time period afterwards, do we get a statistically significant increase in the number of deaths? And we don't have those numbers yet. But so what I was using before is essentially your long-term PM 2.5 average. So essentially, if this is the new norm for California, like Jerry Brown said something to that effect, that this might be the new normal for California, and people in California are being exposed to these smoke events more regularly and at higher concentrations, then we would expect this to have an impact on the average lifetime of people in California.
And if I may add, I think in California, you have to realize a lot of people, it's where they live. So if their buildings burned, the emission factors and the impact of them is very different because it has a lot of toxic elements. And I think there we are uncertain, the response functions that Jeff and others alluding need more work so we can actually, if the buildings are burning, you're going to get exposed to a lot of toxic stuff that's in there. And not that biomass burning doesn't have. So I think there's more work to do at the urban wildland interface and human exposure.
And what about the tree, the flora of there, and is this old smoke, I guess?
Exactly, and mobilization, so what was there before. Fire can be a huge perturbation, and we have a framework. We have a good framework, we've applied it, but I think we need to refine it, as we pose more risk.
But you don't know anything about the flora there right now that's burning, and how that would be different than other wildfires?
Well, I think fire, it would be different, right?
Worse, better?
I think that's why you need research to be able to. I think we always, research resources can add. So we have the tools and the people and so it's kind of resource allocation, and it's important, as you know.
Are there other questions?
From Dr. Eslami. If you could explain to me, what is the PM 2.5 estimated deaths per year at economic cost of wildfire smoke today, and what is it projected to be by 2100, I'm assuming under RCP 8.5? Because I think you've said those numbers, but I'd like to hear them again to make sure.
We actually presented different numbers too, so it's a good thing to discuss. Yeah. So why don't you start?
Yes, hi. The number that we presented here, around 5,000 deaths per year caused by air quality degradation of biomass burning for PM2.5, and the cost is between $40 to $50 billion per year. So that's what we estimated using our modeling system. That's maybe represents for the year 2011 to 2014. So pretty much that any year near this should be the same or the similar number. Yes.
When you say biomass burning, that's mainly wildfires. There's something else in there that I should know.
No, this is only for air quality degradation caused by biomass burning.
Okay. So biomass burning that includes not only wildfires but agricultural burns and
everything. Yes.
Yeah. So I showed a slightly higher number, and in your talk the other day, you showed a second, because you did it a sensitivity, so you showed like 11,000 in that one, and I showed 25,000. And this is uncertainty. In my last slide, I gave that caveat of there are uncertainty in the health response functions that are on that order. So, we're on the thousands of people per year, and I'd say that probably a decent bounding. And we know that 25,000 is on the high side, just that one function from one group that we use, we were aware that was on the high one, and we have planned to be testing the sensitivity to that. For the future projection, so it's 25,000 we put for averaged over 2000 to 2010, and then for 2090 to 2100 we had 75,000. So it was a bit better change. So if you were using the estimate functions that Ebrahim was using, 30,000. And that's a RCP 8.5? That was for RCP 8.5, yep. Though for the U.S. in our projection for that single case with 4.5 and a single case with 8.5, there wasn't a big difference in the U.S. And I don't know if you were in the Björknes lecture yesterday or 2 days ago, the speaker was talking just if you take single model simulations out of even the same model, if you ran it 40 times and you only looked at the U.S., in some case you may get this change where the western U.S. is warm and the eastern U.S. is cool. And so I think that from the single case, there's quite a bit of uncertainty, and we would need more simulations in order to sort of nail that down better too.
Hi, Olive Heffernan. Can
right.
you just explain that a bit?
So these are also in the same representative concentration pathways that are the RCP that Chris just mentioned, and so it's a group of people that try to come together to put together what we think are our best potential futures in terms of what's being emitted in terms of not only CO2 and other greenhouse gases, but also SO2, as well as primary organics and black carbon from vehicles. And so the projected future, and as far as I know, in all the RCP cases for North America show a continued reduction of vehicular industrial emissions that is consistent to what we've seen over the past 30, 40 years, really. It's just continuing that.
Are there other questions from reporters in the room? Are there any questions on the chat? Okay, great. That concludes our press conference. Thank you very much.
Thank you.
Next up at 10:30 is music and geoscience.
Oh, that sounds a lot more fun.